We know previously that a certain number of the second kind talks about the number of ways of distributing n objects into m identical boxes such that none of the boxes is actually empty. For this video, let's talk about some of the important properties that we could use later on, especially when we try to solve for some certain numbers of large relationships. Say for example here, as mentioned, what if, take note, our n is the cardinality of the first set and m is the cardinality of the second set. Okay, so this is actually the form of the certain number of the second kind. So the number of ways of distributing these n objects into m boxes, m identical boxes specifically, where none of the boxes is actually empty. The first property is actually the Stirling of 0 and 0. This is equal to 1. Illustration for that: how many ways to distribute 0 objects into 0 boxes? Since there are no boxes and there are no objects, there's only one way to distribute that: do nothing. Okay? Doing nothing fits the idea that since there are no objects and there are no boxes, that's just equal to 1. Okay? So even if there are no boxes and no objects, the number of ways, okay, to distribute that is just 1, doing nothing. Okay? So hopefully that's understandably, that's actually very trivial, but that is actually how it stands for. Let's talk about the second property, S of n 0. The number of ways of distributing n objects into 0 boxes. Okay, this is where it gets different from the first one. Earlier, it was 0 objects, so 0 boxes. Here, a lot of n objects into 0 boxes. The number of ways for that is actually 0. Don't be confused about the two, because the second one here is you already have the objects and you don't have box, so you cannot do an arrangement. But earlier you have 0 boxes, 0 objects, so doing nothing counts as 1. Okay, hopefully that's understandable here. This is actually true for all, okay, for n greater than or 0. So because if it's 0, it fits the first one. Okay, the third, okay, let's talk about the third property. If arranging n objects into n, meaning the number of boxes matches the number of objects to be distributed. Okay, so how many ways for us to arrange that, considering that none of those identical boxes will be empty? There's only one to arrange that, meaning all of the objects or each of the object will be placed into each of those identical boxes because they match in term of number or count. Okay, and that is actually making sure again that none of those boxes will be empty. So all n boxes will be filled with each of those n objects. Okay, so hopefully that's clear. That's another property that we can draw in. Now let's talk about the fourth rather. So I'm talking about the fourth. Say for example, n and m, where, okay, the number of boxes is between 1 and your n, meaning n is greater than or equal to m, but of course m cannot be equal to 0 because it will fit the first two ideas. Now what if there are number of objects are more, okay, more than a number of objects are more than the number of boxes? So for this situation, our Stirling number will be greater than 0. There is a possibility that it will be 1 if they are equal to one another, matching the third property, or they could be more than 1, thinking that, say for example, you have 5 objects and 4 boxes. In short, there are more than one way to distribute those because the remaining 1 object can be placed anywhere. Okay, but since they are actually identical, so that's another way. There are a lot of ways here as long as the number of n objects is greater than m. Let's talk about property number 5. What if, just like that, m is greater than n? In short, the number of objects, a number of boxes, that's m's. In short, the number of boxes are more than number of objects, how many ways can we arrange those n objects into m boxes, considering that none of the boxes will be empty? The answer for the Stirling of the second kind is 0. The reason for that is, if we're going to distribute n into m identical boxes, but the boxes are more than the objects, some of those boxes will be empty. And according to the Stirling number of the second kind, the idea there is no box should be empty. But since some of them will be empty, so it will not actually be possible. Okay. Now, let's talk about the idea of what will happen if we have close relationships between the number of n, or number n objects, and number of boxes. Now, here comes important properties that you could also use later on as we proceed to solving for Stirling number of the second kind. This next one here. See, what if the number of boxes is only less than 1 with number of objects? So for example, 9 objects, 8 boxes. 3 objects, 2 boxes. Meaning the number of boxes are actually just less than 1 from your objects. It is actually computed as n combination 2. If you have situations like that, simply take the n combination 2 for that result. Another property, if the number of boxes, identical boxes, is 2 less than your number of objects. So this is also computed, for examples, you have 9 and 7, 4 and 2. This is computed as the n combination 3 plus 3 times n combination 4. Okay? That is what will happen for these situations. We'll be using that later on some examples in the next video. And the last one is this. What if it's very large? Very large, and then we don't have these relationships for that. So for example, starting off number of the second kind for 50. That's very large, right? Or let's say just say 10 objects into 7 boxes, identical boxes. So this is actually called as the recursive, okay, recursive relation. We can break down the problem into smaller aspects, because if we have here, say for example, n of k, which may think that they are large, so this is actually k times Stirling of n minus 1 and k plus the Stirling of n minus 1, k minus 1. Okay, this is the formula to solve a Stirling number of the second kind where n and k may be large. Why is it called recursive relation? Because the idea here is, what if this one is still large and this one is still large? So you still need to look into the formula for this and for that. And what if again there exists Stirling number of the second kind which is actually very large? So break it down and so on and so forth. This may be used for some instances, and we can also use this relationship as we move forward for this. These are the properties for the Stirling number of the second kind, which may be applicable in distributing a number of ways of distributing n objects, n distinct objects, into m identical boxes, such that none of those boxes is empty. Thank you very much for watching.